How you doing, everybody? I'm Mr. Rose, and today we're going to talk about Newton's laws and friction. More importantly, we're going to talk about the inspiration for games like Champ Ramp. Now, Champ Ramp didn't just come out of nowhere. It was a building process, and before we got Champ Ramp, we had, you see it right there, balance blocks. Now, balance blocks, very complicated game. What we got to do here is we've got to push block A with such a force. In fact, we want to know the maximum force that we can push block A with such that block B doesn't move. If block B moves at all, you lose the game. This may not be as exciting as a game like Champ Ramp, but we're going to get after it right now. So I got a camera over here. I got a camera over here. I'm going to be moving around. We're going to do the best we can. Here we see my setup, right? And my setup just has block A and block B. Now, in this game, I'm not going to tell you what the masses are of each block, and that might change as the game progresses. So to do this, what we need to do is we need to figure out what exactly it is we need to examine. I am going to do my best to color code. So we have three possibilities. We can look at block A, we can look at block B, or we can look at block AB, right? So scenario 1, I can examine block A. Scenario 2, I can examine block B. And now, oddly, scenario 3 is probably the one you're all like, yeah, let's do that one already. I got block B on top of block A. Now, it seems like scenario 3 would be the best one to use, right? Because this is what we're looking at. But I'm here to tell you that's kind of the sucker's choice. We are actually not going to look at scenario 3. We're going to examine scenario 1 and scenario 2, right? Now, I'm out of room here. So the reason why we're going to examine those two scenarios are because, sorry, I just want to be able to see that, is because we can only examine one situation at a time, right? So if I look at both of them, that's going to get a little bit too complicated. So I'm first going to start with block A, right? Let's see, there we go. First, going to start with block A. I'm going to start with block A because block A is on the bottom, and more importantly, block A is before block B alphabetically. Nothing to do with it. It's actually just because it's on the bottom. And I'm going to identify every force acting on block A. All right, so every single force. So I'm looking at scenario 1 and 2, every force. So there's block A. I already wrote that there. I'm going to put my coordinate system in because we know we need an XY coordinate system. And first thing I'm going to do is I'm going to go with the ones I know right away. I've got the normal force, N. And I'm not just going to label it N. I'm labeling this N. This is the ground acting on A. And there's a reason why I'm being so specific here. We know we had the applied force. That's what I am pushing it with. I think I already messed up my color codes. Now I have, use those two. All right. Now we have, well, obviously there's block A. There's the force due to gravity, right? So I'm going to say I've got an MAG. That is the force due to gravity of block A. But block B is on top of block A. I need to include that. MBG. There we go. I'm running out of colors here because I have two more forces. Well, the next one I need is the friction. There is a frictional force on block A, and that frictional force is the ground on A. And that's another orange. Guess I'm going to do a dotted line. Let's do a dotted purple. 1, 2, 3, yep, that's all I got. Dotted purple. What is that dotted purple one? That is a friction. That is the friction of B on A. Now notice the direction it is and think, why is that the direction? That is the B on A. I'm not going to tell you why that direction is going that way. I want you to think about it. What direction does friction go? Remember, friction always opposes motion. So we've got my applied force. we've got the mass of B on, oh, that shouldn't be the MBG, sorry. That is the weight of G. This here, MAG, that's the weight of A. This is the frictional force of the ground on A. This is the frictional force of B on A. And this is the normal force, the ground on A. Now, don't be confused. Obviously, there is no normal force here for, what's it called? For block B. And now we're going to add block B here. So, block B is a much simpler free body diagram. Block B, we only have 3 forces. We have, remember these are important, I have dotted line, and that is the action-reaction pair. This is FA on B. The frictional force of A on B. What direction is the intended motion of these blocks? So hopefully now we're seeing where we're going. Then I have a normal force, right? That is my normal NBA. Yeah, that is the normal force of block B sitting on block A. And then we have, oh, I totally messed up my color codes. I guess I'm just going to go here. And this is just MBG. That is the weight of block G. Again, since this is a different free body diagram, we technically need a new XY coordinate system. So I want to try now and match up our pairs. And when I match up our pairs, looking at the screen, not the camera, when I match up the pairs, we want to pair up our interactive pairs. In other words, our action-reaction forces, right? So we have, let's see, MBG and NBA. Those are my action-reaction pair. So I know the magnitude MBG is equal to the normal force of B acting on A, right? And then I also know action-reaction, my dotted, F friction of B on A, friction of A on B. Those are also my action-reaction pairs. So I'm going to say FB on A is equal to FA on. All right, so now where are we going here? Now we have all of our magnitudes, sorry. And now that we know this, we can try and eliminate some of our subscripts, I don't want to say useless subscripts, but the arbitrary subscripts for things that we actually know. In other words, like NBA, that's just the normal force. That's the normal force of block B, right? So I can just say, I'm going to let NBA equal just the normal force acting on block B. What else do we know? We know that the frictional force of A on B, what frictional force is that? The frictional force of A acting on B, remember, block B is the one that's supposed to be stationary, right? So that means FA on B has to be static friction. So, is that the right one? Yeah. FA on B is actually my Fs. That is a static frictional force. And block A is moving, which means block ground on A, that one right there, F ground on A, that is Fk, or my kinetic frictional force. And now that I know all of this, I can start to apply Newton's second law. So jot all of these things down. Keep my action-reaction pairs handy. And we are going to apply Newton's second law. I got markers or pens all over the place, right? So I'm going to apply Newton's second law. And I'm going to apply Newton's second law to both blocks. I'm going to apply it to block A, and I'm going to apply it to block B. So first I'm going to look at block A, again, because I know alphabetically block A comes first. So I say the sum of my forces in the for block A is MA times the acceleration on block A. All right, well, what do we know here? I know that this guy right there, this is, sorry, I had a moment there. I know that FA is, again, I want to do this way. I want to look at it, and this is going to be silly, but I want to examine the block A in the X direction and in the Y direction. And you might be thinking, Mr. Rose, we don't need the Y direction. I think we're going to need the Y direction, right? So let's first do, I got that little here. Let's first do the X direction for block A. Remember, block A, again, is on the ground. So this is the sum of the forces in the X direction. For block A is mass A times the acceleration in the X direction of block A. And let's just do this one first. Now, the free body diagram that I need to refer to is here. So you should have that free body diagram. I will try and keep my colors going. I should have my applied force, that's F. Right? Let me remind us of our coordinate system. So my applied force, F. And then I need to subtract off what we are calling the kinetic friction and the static friction. Remember, those are all these pairs that we put together. So I need to subtract off the kinetic friction and the static friction for block A. So that is going to be minus Fs, color is minus FK. All right. That is everything in my X direction. Now, don't forget about the opposite side. That equals the mass of my block, obviously. The mass of A times the acceleration of A. Now, I said I wanted to look at the Y direction too, and you're like, yo, Mr. Rose, why do I got to look at the Y direction? Like, it's 0. The acceleration is 0, and that's true, but I got a whole lot going on in the Y direction. What do I got going on? I've got, again, free body diagram. I've got my normal force, and that's going up. So I've got the normal force of the ground on A. Then I got to subtract off MAG and MBG, right? So I've got to subtract off minus MAG minus MBG. That looks like it's about it. And that whole thing is equal to 0. Now, the reason I knew we needed that is because we are dealing with friction, and we know at some point friction's probably going to need some normal forces and such like that. I'm going to stop here. I'm going to put half boxes around these because I think these things are going to be important, right? So now as I go on, I want to look at block B, still on the screen. I want to look at block B, and block B, we're going to do the exact same thing. I want to do an X direction, and I want to do Y direction. So in the X direction, I know for block B, the sum of the forces is MB times A, and I'm going to keep it in the Y direction. The sum of the force in the Y direction, that should be an X, is the mass of block B times the acceleration in the Y direction. Now again, we know this acceleration in the Y direction is going to be 0. Block B is the easier of the two to deal with. I know block B is just going to be the only force in my direction is purple. That is FA on B, which I called which is the static force. That is the only force in my X direction, and that is just going to be equal to BA AX. And then in the y direction is a little bit more complicated, but not a ton of more complicated. I've got NBA, so that is the normal of B. And actually, I still call this GA, and we'll explain that why. So then I have the normal of B minus, that's just pencil, minus MBG minus MBG is equal to 0. So this was applying Newton's laws. All right, so now I've got these 4 equations. What the heck am I going to do with them? Well, it's simple. I'm now going to be able to outthink my way to the championship, win gold medal on my way to possibly a double gold in champ ramp. So what do we got to do? We've got to remember something. We've got to remember the frictional force. And how do I solve for the frictional force? Now remember, we're trying to push this block. There we go. Trying to push that block. This block right there. This is what we're doing. We're trying to push block A with the maximum force such that block B doesn't move. So, in order to do that, I need to find Fs max. Is that on the screen? Yes. Fs max, and I know to find that, that is equal to mu s times the normal force. Now, this normal force is, sorry, not the normal force. This guy right there, this is between my surfaces. And I've got a lot of surfaces going on. And what's it called? I'm looking between the surfaces of block B and block A. I'm getting confused in my own game here. So the other thing is the normal force. What normal force are we talking about? We're talking about the normal force of block A and the surface. So we're going to look at block A, we're going to look at block B, then we're going to look at friction. We're going to put everything together. You shouldn't need as many pages as I do for this. So, oh man, my colors are going to be all sorts of messed up. I'm going to say back to block A. All right, every equation, yeah, I'm going to put all of my equations on the same page. I'm going to fast forward through this. You're going to see me write really fast. It's going to be awesome. All right, there are all my formulas that I have. I simplified a little bit as I went, and I did mess up my colors, my bad, but it was really cool to watch me write all of that as fast as I possibly could. Now that we have that, we're going to simplify some things. Well, what am I going to simplify? Well, I mean, I know F equals ma. That's kind of a good place to start. And, well, oh, look, F equals ma right there, this one. I'm going to simplify with this and find the acceleration. Why am I going to do that? Because all of the accelerations here are the same, right? Everything's moving. Now, be careful, because depending on your reference frame, block B, the one on top, might not actually be moving, right? So I'm looking at the acceleration of block A if I really need to talk about it. Because with respect to block A, block B, the one on top, ain't going anywhere. So I'm going to take that frictional force and I'm going to solve for A. More importantly, I see a lot of A's, so I might be able to sub some things in. That's kind of where I'm going as well. We want to start with the simplest thing. So I'm going to just rearrange that sucker right there, and I'm going to say that A is equal to purple divided by, oh, my colors are all off. It's very sad. Good thing that our game has nothing to do with colors. And now I can sub in my acceleration. I'm going to sub that into my force equation. Wait, my force equation? What force equation? Bang! My force equation right there. Oh, I realize. Yeah, well, that doesn't matter because it was the same. I transcribed some FKs and FSs, but everything's subtracting, so it doesn't matter. That was lucky, not a lucky. I was lucky. So I'm going to say, what am I going to do here? I'm going to say that F minus my FK, dark, FK minus my static force. that guy is equal to the mass of block A times the acceleration, which we just happened to find, of Fs over mass of block B. That happens to be my acceleration. Now I'm going to have a big substitute. I'm going to try and substitute for all of my Fs's and all of my Fk's. In other words, getting rid of the frictional force and the static force for mu times the normal force. Remember, I told you that I was going to need those normal forces? Now I got them because I know I'm going to try and do it in one step. Hopefully I don't mess it up. I know Fk is mu times the normal force, bang. I know Fs, mu times the normal force, bang. So I'm going to have a big substitute in here. I'm going to say all right, now there is one more step because that can simplify. I'm going to pause because I don't want to make a mistake. I'm back. I don't like what I did. Up here where I have block A, I simplified some. I didn't simplify enough. And it's silly. This is nice and easy. I'm just going to do it real fast. I want this F equals because I'm trying to find F. I kind of lost sight of my problem, right, in my good storytelling. So I'm going to simplify real fast and then resubstitute. It'll actually be somewhat easy. So this is going to be F equals Fk plus Fs plus Ma. Then we're going to have that big substitute. So, right, I'm going to have F equals, that's going to be plus now because I'm bringing it the other side, so sorry, plus Fs plus Ma, and now I am subbing in for my acceleration of the frictional force divided by, I totally just lost all of my colors, MB. And now that a reason I did that is you can see this has a frictional force here, frictional force here. Now when I have my big substitution, this is what I'm also going to attempt to do in my head, just because this video has been running on for a long time. With my big substitution, I am going to have something like, I'm going to try not to mess up my colors here, just because I think it's easier for you to follow. On camera, yes. I'm going to have something like F equals, I'm subbing in for that, Fk, so that is this blue, mu k times mag plus mbg. That seems right. And now I'm going to add, all right, I'm not good with my colors, but I have one color, so that's good. Now I'm going to add mu s, and this is where I've got that guy and that guy, so I'm going to have a factor of a 1. So I'm going to have something like mu static times mbg times, that's going to go in there, I can factor 1 plus ma. That's it. That, my friends, is the winning combination to balance box. Yep, it doesn't matter the masses, it doesn't matter, it could change. The masses of the boxes could change, the size of the boxes could change, the surface of it could change. All we need to know is exactly what's going on with our scenario. Bam! And I can calculate exactly how much force I can push it, such that the box on top, box B, does not move when I push box A. That's all I have for you today. It's been a long journey. This is an all said and done editing, probably a good 20 to 25 minutes, so thanks for sticking around. I hope you tried this before you watched me do it. And keep watching for the new Olympic Games, We need some time, so probably Olympic Games, maybe 2026. I think that's an Olympic year. We'll get right to it. Please feel free to like, click, or subscribe to YouTube, and you'll see me here next time.